week 4, part 1 of our physics lectures. And today I'm going to talk about dynamics. Dynamics is the study of forces that cause objects and systems to move. So previously in kinematics we were studying the motion of objects. Now we're going to look at the things in life that cause motion. The importance of observation and cause and effect were not always a given in human thinking. But Newton, as much as any other single individual in the history of mankind, produced achievements that were milestones in the development of these concepts. This book, which is simply called the Principia, is his contribution to the mathematics of physical motion and dynamics. In the space of 18 months, he actually wrote 4 treatises on physics, including this book, as well as a book on optics and planetary motion, which revolutionized the thinking in science and physics. For this reason, many people believe that Sir Isaac Newton was one of the 4 most influential scientists to have ever lived. So when we talk about dynamics, we have to talk about something called the force concept, or forces in action. On the left, you see a real-life diagram from above of 2 people exerting 2 different forces on an individual, force 1 and force 2. And as with all vectors, there's the sum of these 2 vectors shown and called FTOT. This can be represented by what's known as a free body diagram, in which you isolate a point and show all the forces acting on that point. A force is any influence that causes a push or pull on a system or an object. And you have to define the system or the object. And one of the examples I go through, you'll see the importance of defining the system or object involved. The free body diagram, which, as I said before, is on the right, is an illustration of all external forces acting on a single point, which represents the body in question. Now, Newton had 3 laws of motion. And the first law of motion is illustrated here. Newton's first law of motion states that a body at rest remains at rest, while a body in motion remains in motion unless acted on by an outside force. So A represents a spring system which will remain as it is without any outside influence. B represents someone exerting an outside influence on that system, and how if he releases his exerted force, there's a force that will restore it back to its original configuration. Inertia is the property of any mass or any body to obey the first law of dynamics. The mass of an object is the measure of a body's inertia, and it's also equal to the amount of matter within that object or body. Newton's second law of motion states that force is equal to the mass times the acceleration of any body. So a force operating on a system causes the system's mass to move, and that system's mass moving will accelerate until the force is dissipated or removed. In the top you can see 2 young individuals pushing another individual in a wagon, and you can see beside it is a free body diagram representing this system, where you have the weight pushing down, the normal force pushing up, and we'll talk about that when we talk about the third law. you see a force 1 and a force 2 being exerted by the two individuals, and this results in an acceleration which is proportional to the mass of the individual in the wagon. Similarly, the second diagram shows a single individual pushing a person in a wagon, and it is meant to represent the fact that the single larger individual, if she exerts a equal force to the two smaller individuals combined, results in the same net force and the same acceleration. It is the net external force that leads to the acceleration, and by that I mean the net will be, in this case, these two forces in this direction minus the force of friction in this direction. The net here, up and down, is always equal to 0, which is why the wagon doesn't move up or down. Similarly, the net here is this larger force exerted by the adult subtracted by the force of friction. An external force is any force that's applied that's not considered part of the defined system. So if we draw a circle around the defined system, which in this case is right here, then these two forces exerted by this individual are considered external forces. Now, since my computer seems to want to go to the next slide, let's go to the next slide. And the purpose of this slide is to show what happens if the same force is exerted on two different objects of different masses. What occurs is, first of all, if a basketball player pushes a basketball to make a pass, and the mass of the basketball is m1, then you achieve a certain acceleration, a1. If, on the other hand, the same player exerts the identical force on a stalled SUV, because the stalled SUV has a mass m2, and because mass m2 is significantly greater than mass m1, the resulting acceleration of the SUV is considerably less, even though the force is the same. The free body diagram of these two incidents would be identical, which allows for the comparison of the two situations. When you draw a free body diagram, the mass is not necessarily taken into account unless you are showing the weight of each object. Now let's take an example of the second law of motion. Here we have an individual pushing a lawnmower, and I'm going to tell you that the net force is 51 newtons to the right. At what rate does the lawnmower accelerate if the lawnmower has a mass of 24 kilograms? Well, this is quite simple. And what we see here is if we say F net is equal to ma, then the acceleration is going to be equal to F net divided by m, or 51 divided by 24, which results in 2.1 meters per second squared. A newton is a kilogram meter per second squared, so the kilograms cancel each other out, and that results in an answer of 2.1 meters per second squared. Here's another example. This is a jet car or a jet sled, and what we see here, it's powered by 4 identical rockets, each producing a force labeled T. If the sled and the pilot have a mass of 2,100 kilograms, what value of T, realizing it's 4 times T that results in the acceleration, will produce an acceleration of 49 meters per second squared? Friction force is equal to 650 newtons. And you see again the free body diagram shows the weight of the cart and the sled and the driver here, the normal force, which is the force pushing up on the sled, preventing it from sinking into the earth. There's 4T forces in this direction driving it forward, and a friction force driving it in the other direction. And all of this results in an acceleration of 49 meters per second squared. Well, if we look at this, again, the acceleration is going to result from a net force, and the net force is going to equal 4 times T minus friction. So 4 times T minus friction is going to result in a mass times the acceleration. We have 4T minus 650. The mass is 2100 and the acceleration is 49. And if you solve this equation for T, you get 2.5 times 10 to the 4th newtons. Now this diagram is illustration of the third law, and the third law is what causes the normal force that I kept mentioning in our previous slides. And what we have here is a swimmer who pushes up against the wall and causes motion from right to left. The third law states that whenever one body exerts a force on another body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that is exerted. So for example, here we have an individual. They're going to push their feet on the wall, and they push with a certain force F. And at the same time that they push with the force F on the wall pushes on their feet with a force, causing them to move in this direction. Now the only force that has to be put in the free body diagram is the force of the wall on the person's feet, because it's what results in motion. Here, to be complete, we also have the weight of the swimmer, and BF stands for the buoyant force of the individual. And they've drawn a circle here around the swimmer, and the swimmer is the individual that is the system of interest. Now with that introduction, in the next part we're going to go through several problems and work through several problems.